Good morning. This is Mrs. Doris. If you are absent today, this is the warm-up that we are doing in class. It will take just a moment or two of your time. So pause the video at this point so you can complete the warm-up. We are also working today on page 237, problems 5 through 21. This is slightly different from your assignment sheet, which says 5 through 23. We are not doing 23 since we did not cover the last part of chapter 2. We are going over our stories to graphs that we started yesterday in class, so make sure that you have completed this for your chapter 4.1 notes. All right, today our lesson is 4-2, Patterns in Linear Functions. Our objective is that you will be able to identify and represent patterns that describe linear functions. We are studying functions because they can be represented in many ways and are very important to mathematics. All right, we talked a little bit yesterday about our independent variable and our dependent variable. The independent variable is always our x, and it goes on the horizontal axis. In mathematics, we call this the input. The dependent variable can change in response to the input. The dependent variable is represented by the y variable, and in mathematics, we call it the output. A couple of vocabulary terms today. First of all, function is simply a relationship that pairs each input value with exactly one output value. Another way of saying this is for each value of x, we get exactly one value of y. A linear function is simply a function whose graph is a non-vertical line or part of a non-vertical line. Our steps to representing a linear function are as follows. First of all, you want to make a table using x as the independent variable, y as the dependent variable. Next, you want to look for a pattern in the table. Describe the pattern in words so that you can write an equation to represent the relationship. And then you want to use your table to make a graph of the function. All right, so our first problem is representing a geometric relationship. And the first thing that we're going to do is make a table, which has already been started for you. So notice we have one square, and its perimeter is 1, 2, 3, 4 units, and that's already been shown for you right here. Two squares has a perimeter of 1, 2, 3, 4, 5, 6. All right, which is already in our table. Three squares, and you may begin to see the pattern here. We have 1, 2, 3, 4, 5, 6, 7, 8 would be our perimeter. And when we have four squares, it may be interesting to note that we have 1, 2, 3, 4, and 1, 2, 3, 4 on our top and bottom. So 2 times 4. And then we have our left side and our right side in every case. So that would be a total of 10. All right, so we want to find a relationship so that we can use words to describe it, and then we're going to write an equation and graph it. So if you notice our squares, it looks like we have, for two squares, we have 2 squares along the top and bottom. So we could say in words that you multiply the top by 2, or I'm going to change that. Let's multiply the number of squares. Multiply the number of squares by 2, and then you notice we added on the left side and the right side, and then add 2 for the left and right side. And I didn't give myself enough room to write that, but squeeze it in if you can. All right, so when we get down to 10 squares, we would want to take 2 times 10 for the top and the bottom, which would give us 20, plus 2 would give us 22 for our perimeter. If we had a perimeter of 62, notice what we would have to do is, to find our number of squares, is subtract off the left and the right side, which is 2, which would give us 60. And that 60 is going to be split evenly between the top and the bottom. So 60 divided by 2 would give us 30 for our number of squares. And writing an expression for any number of squares, which we'll call n, we're going to use our rule that we wrote in number 2. We're going to multiply the number of squares by 2. So 2 times n, and then add 2 for the left and the right side. Okay, so here we have our completed table, and we are going to write, we did not write our equation. Let's write our equation before we graph it. All right, so notice that perimeter being our y and number of squares being our x, we would write 2 times the number of squares plus 2 would be equal to our y. All right, now let's graph it. Okay, so number of squares is our x and goes on the horizontal axis as our independent variable. And the perimeter is our y and goes on the vertical axis like this. If we wanted to give it a title, we could call it perimeter of squares. All right, now we need to give it a scale. I'm going to start with 0, of course, in the corner, and each square is going to represent 1. So you don't have to show all the numbers, just make sure that you space them evenly so that you have it. So, all right, that should work well for us there. I'm going to do the same thing along the vertical axis so that each square represents 1 unit. All right, so our first ordered pair is, if we have 1 square, we have a perimeter of 4. If we have 2 squares, we have a perimeter of 6. 3 squares, a perimeter of 8. 4 squares, a perimeter of 10. And we can continue this. 5 squares, we would have a perimeter of 12. 6 squares, a perimeter of 14. And there you see we want to connect our dots in a straight line, and we'll put an arrow to show that this will continue. All right. Any questions? Please ask in class. All right, problem 2. we're going to represent a linear function. So we're going to graph each set of ordered pairs separately, and then we'll use words to describe the pattern shown in the graph. Does the graph represent a linear function? All right, so here we go. We're going to use red. I'm going to just number these. Number 1 will be the first set of numbers. So I'm just going to label my axes X and Y. 0, 0 would be right here. Again, we're going to use basically a similar scale to what we did on the previous problem, although we could spread them out a little bit more if we wanted to. All right, so here we have 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. All right, so let's describe this function. As x increases by 1, what happens to the y? Well, it increases by 1. So as x goes up 1, y goes up 1. Increase x by 1, y goes up by 1, and so forth. So let's describe it. As x increases by 1, y increases by 1. All right. Does the graph represent a linear function? And the answer to this is yes, it does. It is non-vertical, it is diagonal, and the points lie in a straight line. So it is a linear function. All right, I'm going to erase this one, and we're going to graph the next one. I'm going to use blue for the second group. So we have 0, 8, 1, 6, 2, 4, 3, 2, and 4, 0. And again, I'm going to connect them with a line. These lie in a straight line. And how do these compare? Well, what we notice is that as x increases by 1, y decreases by 2. So we're going to write that as x increases by 1, y decreases by 2. All right, and you'll notice that pattern continues. As x increases 1, y decreases by 2. As x increases by 1, y decreases by 2. All right, so here you have, as opposed to number 1, which was increasing, number 2, we have a graph that as x is increasing, y is decreasing. All right, so I'm going to erase that, and let's go to our third group, and we'll use green to graph it. We have 3, 0, 3, 1, 3, 2, 3, 3, 3, 4. So you can see these lie on a vertical line, and what we notice is x is always 3. All right, so y can vary, but x does not vary. So x stays the same, and y can be anything. All right. This is not a function, and I guess we ought to label these. Number 1 was a function because it was a straight line. Number 2 was a function because it was a straight line. Number 3 is a straight line, but it is not a function because it is vertical. And to be a linear function, it must be non-vertical. All right, let's try some problems on page 243 and 245, 7 through 19, the odds. And if you have any questions, please ask.